position is very important. So that's why when you have u plus u prime multiplied with v, we write uv plus u prime v. Similarly, u multiplied v plus v prime, we write uv plus uv prime. So the position is extremely important here. There should not be any this one. However, if you multiply some real value to this tensor product of u and v, it can go with either any one of the vector. So for example, if you have some linear operator a which takes u to u and b which takes v to v, that means any element of u can be transformed into any other element which also belongs to u. That transformation operator is a, and similarly for any element in v will be transformed or translated into the any other element which belongs to v, then we have that particular operator that is given as b. Now this a tensor product b operator acting on uv means that a should act only on the first particle and b should act on the second particle or second vector. Remember, a will act only on u, b will act only on v. So it is actually, if you want to break this one, it is basically a tensor product b multiplied with u tensor product v. So therefore a should come with only u, b should go with v. So therefore we have this particular operation. And when you want to write, when you want to obtain this tensor product multiplication, what you have to do is that, sorry, this one should be a tensor product b. When you do have a tensor product b, this means that you take entire b matrix and then multiply with each element of the a matrix. That is, a11 is multiplied with b. If a b is a 2 cross 2 matrix, then you will have a 2 cross 2 block here. This will be a 2 cross 2 block. Similarly, you can do this one. For example, if you have 1 0 0 2, which is a 2 cross 2 matrix, and then if you have b as equal to 1 times 1 cross 3, then you have to take a11, which is 1, and multiply with entire b block. So therefore you have 1 2 3. Now again you have a12, which is 0 into entire b block. So therefore b matrix, that is, you have 0 0 0, and you have again a21, which will give you, multiplied with b will give you 3 zeros, and you have a22 element which is multiplied with b matrix, that therefore you will get this one. Therefore you will, when you multiply, when you have a tensor product of a cross b, then you will get a 2 cross 6 matrix corresponding to these two matrices. So in general, A is n cross m matrix, and then B is n prime cross m prime. Then we have A tensor product B is written as n prime and then m prime dimension. So now we are ready to talk about bipartite quantum system or 2-qubit quantum systems. Two physical systems, say some A belonging to which belongs to Hilbert space A, and then B which belongs to Hilbert space B. Then the whole composite system, like we want to write the we don't want to address these two physical systems or 2-qubit system as a separate qubits, but I want to write it as a total system. So for example, if you have a spin up and spin down particle, okay, of a spin off particle, spin up and spin down as the quantum state of a spin off particle, then I don't want to address them individually. Rather, I want to write a wave function corresponding to these two particles as a collective one. So in such cases, the Hilbert space corresponding to this one is written as HA tensor product HV. So you have to write the tensor product of these Hilbert spaces. So if you have a orthonormal basis which is identified with respect to first Hilbert space, that is HA, and then if you have a orthonormal basis set which is identified with respect to the second Hilbert space of the second particle, then the total Hilbert space can be identified as IA tensor product IB, and which belongs to HA tensor HB. So this is what is the Hilbert space corresponding to the bipartite quantum system. So for example, if you consider a qubit A and qubit B, which is from the both of them are from Hilbert space A and Hilbert space B, then we have this one. If you try to write the wave function, general wave function in with respect to the Hilbert space A and Hilbert space B, the two qubits can be written like this. So I have taken arbitrary alpha beta as the mixture parameter for these two states, okay, and similarly gamma and delta for in the Hilbert space B. So now if you want to write a composite system which is made up of both the particles, okay, then you can write this one as a HA tensor HP. So basically it is writing your wave function as equal to tensor product of the wave function of particle 1 and a wave function of particle 2. So now we write the tensor product, and when we write the tensor product, I'm just writing these expressions over here. Okay, now we have four terms coming into picture. So therefore I will write alpha gamma, okay, and then 0a tensor product 0b. Similarly 0a tensor product 01, 1b, and I have 1a tensor product 0b, and then I have 1a tensor product 1b. So these four terms are there. So instead of writing this tensor product of two entities, we club together and then we rewrite in a new notion, that is 0a 0b. This is means that the R, I can rewrite it as 0 and 1, 0 and 0 here. You can see that in the fifth line, that the last line that I have written 0 0, this means that, as I was emphasizing earlier as well, the position of this notion is very important. This corresponding to A, the second bit, second qubit, second 0 corresponding to B. Similarly, this in the second term, the first position corresponding to A particle, second position corresponding to B particle, and so on. So therefore, I have a general 2-qubit state which can be written as A 00 plus B 01 plus C 10 plus D 11. And of course, our normalization should be taken care whenever you write any density in any state. So once we have a 2-qubit system, okay, so then can we write? We can eventually identify its matrix structure as well. And so here 0 0 means it is nothing but 0a tensor product 0b. So corresponding matrices are given as given by this expression matrices, and you know how to do the tensor product. So first element into the second matrix, second element of the first matrix into second entire second matrix. So therefore we have a 4 cross 1 matrix obtained. So when you obtain 4 cross 1 matrix for 0 0 0 1 1 0 and 1 1, you add up everything, you will get the psi AB in this form. And if you want to write the density matrix, of course density matrix can be obtained by the outer product, which you can check that this will come out as this 4 cross 4 matrix. And of course the normalization demands mod A square plus mod B square plus mod C square plus mod D square is equal to 1. And also you can see that directly, you can see that the trace of this particular density matrix is equated to 1. So hence it is a valid density matrix. So now if you want to some specific physical examples, then if you consider a two-state particle, say for example in case of spin-off particle, you have up and down state, or if you want a polarization of the photon, then you can have horizontal and vertical polarizations. So all these states correspond to are the state of the particle is a superposition of the two possible states. Okay, so when they are equal probability, then we have these particular set of 4 set of particles. So when you have a spin-off particle, you can have up up down down, or up up down down with a phase, and then down up down, and down up down with a phase. So the first 3 are called triplets, and the last one is called the singlet. So this set of these 2-qubit states will form a basis. Basis means, recall that they are mutually when mutually ortho, like they are when you take the same vector with the inner product with the same vector, then you will have normalization, that is they should give you 1. And then when you multiply, when you take an inner product of any one vector here with the others, it will give you 0. So therefore orthonormality is always satisfied. So therefore this set of these four different 2-qubit states that I have written here will form a orthonormal basis set. Okay, and these bases will belong to the 2-qubit Hilbert space, okay, which is given as H2 cross H2. Okay, and they are called the famous Bell states. Probably you have already come across these Bell states. So Bell states are the very good examples of the 2-qubit states, a standard example which keep coming often. Whenever you have a qubit and a quitet system, so remember qubit is a spin-off particle with two possible superposition states, and quitet is a 3 possible superposition states. So therefore I can have 0, 1, 2 as the possible representations. Okay, so now if you have a qubit and quitet system, how do we write the composite system? To write the composite system, it is exactly same. You have psi A, psi B, which is nothing but your psi A tensor product psi B. Okay, so now you write the psi A and psi B, and then individually start writing this one. Alpha, alpha, gamma, I will write it, replace it some A, 0, 0, 1, 0, 1, 0, 2, and then 1, 0, 1, 1, and then 1. Please note that here, always the first qubit represent to the qubit. Okay, first state in the given 2-qubit kits that I have written, always the first one will represent to the qubit A, and the second one will be for the quitet state. So this has to be clear. This clarity you should have. Like when I write a ket, a 2-qubit ket, or later on multi-qubit ket, always the position represents the corresponding qubit. So when it comes to multi-qubit systems, consider a mixture of several quantum systems, and they have different dimensions. I don't want to restrict myself to qubits. I can have qubit, some quadrate, and so on. And it's basically you have a mixture of all these different dimensional quantum particles. So then you can write the entire Hilbert space of that particular mixture as a tensor product state. Okay, so if you just consider 3-qubit state, that means I have 3 qubits. So H2, H3, H1, H2, H3, they are all belonging to the same. So all of them have the same dimension, that is they all belonging to the Hilbert space of dimension 2, that is qubit. So when we have this one, a 3-qubit state can be written as a general 3-qubit state can be written as 0, all the possible orientation for the qubit. So you know that qubit will contain only 0 and 1. So therefore we have all the 3-qubit states are there. So there are 3 particles. So if you have 3 particles, 1, 2, 3, then you have 3 particles, then all the possible combinations will be 0, 0, 0, 0, 0, 1, and so on, up to 8 states are there. So this is what I have written here. So I have 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, and so on. Remember here, I want to emphasize again, this one, the position of the particle in the ket is given by the corresponding qubit. So therefore, a 3-qubit state can be written in this way. Similarly, if you have 4-qubit state, then you will have much more terms. So 16 terms and so on. So you can write a general state for any n-qubit state. So in 3-qubit Hilbert space, okay, which is given like this. We have a general, very general states which are called as the GS state and then W state. Just like how you have Bell states in the 2-qubit Hilbert space, we have a very general states which are called as the GS state and the W state. GS state is a superposition of all the particle being in the down state. For example, if you have all the particles are being in the ground, in the spin-off particles, then all the particles should be either in the 0 state or all the particles should be in the excited, or all the particle will be in the down spin down state, or all the particle will be in the spin up state. So if they have such a superposition state is considered, then that one is called as the Greenberger-Hahn-Zeilinger state. And you have one of the particle having opposite spin when compared to the others, and you take the permutation of that particular possible states. So such systems, such permutations of the particles where one of them is having the opposite state when compared to the others, such and its superposition is called the W state. These two are the very standard examples of the 3-qubit W states, and you can write the same GS state for the 4-qubit as well, and the W state can also be written for 4-qubit or any n-qubit. N-qubit GZ and n-qubit W states are possible. So here is the n-qubit GS state. If you have n qubits, then you have all n qubits being in the one possible state, same state, and the other one, other possible same state for the same n qubits, and its superposition. And W state is the one which has one of the particle having the state, quantum state, probable quantum state opposite to all the remaining states. So we have all the permutations of that particular system. So this is called the n-qubit W state. Okay. So similarly, you can write for any other possible. There are several n-qubit states are possible. So like Dickey states and Jaynes-Cumming model states and things like that. So anybody can, like there are several structures depending on the how the angular momentum of the quantum states will tell you about the quantum state. So you can write possible states. So I'll not get into those things because I have to stick to my 2-qubit mixed state. Now let us come to the 2-qubit. I will now concentrate on the mixed state. Till now, whatever state I wrote about the 2-qubit states were of pure state. So similar to single qubit mixed state, a 2-qubit mixed state is defined as like this. So it is exactly same definition. The definition is same here. Okay. However, here psi i's are represent the 2-qubit states, so which belonging to my HA tensor HP Hilbert space. For example, Bell mixture, which is also called as Werner state. You take a row as you are just expanding this one, psi minus. Psi minus is nothing but 1/√2 into 0, 1 minus 1, 0 state. Okay. Similarly, psi plus, which will have plus over here, and then phi minus, and then phi plus. Okay. So these all 4 possible states are added, and you will obtain your density matrix. This is called the mixed state. Some the other forms of mixed states are also possible. Say for example, you have all this Bell mixture. So you have considered 1/4 times like equal probability of psi, the state being in the mixture of psi minus, and so on. Okay, and then you have 1 minus p times psi minus. So there is a probability of this 2-qubit state being in the mixture of this one. That is equal probability, or it will assume only one of the states psi minus. So if you have such a system, then since they are these all these four states will are mutually orthonormal, so therefore they form a basis. So the sum of all these outer products will give you a identity. So hence you can write this one as you can rewrite this above expression as rho w times p divided by 4 into I4 and 1 minus p times this. Okay, so here this is called sometimes as white noise. Okay, if you have basically what the importance of this mixed state definition is also can be emphasized here. Physically, when you try to create a quantum state in the lab, okay, say you are trying to generate a Bell state psi minus, then always you know that the quantum state will be disturbed by its environment. So the disturbance in the environment is chaotic in nature, and hence we call this one as a noise associated with that particular state. So that's why we always have a mixture of the state. So that's why it is also clear why I called it should also be like analogy of calling the universe as the only pure ideal pure state is also clear from here. If you consider any quantum particle in the universe other than the entirety of the universe, then we always have a environment acting on the quantum particle, right? So therefore, we don't see any pure state in our laboratory. Always we have a mixed state, but experimentalists will do some tomographic analysis to create the pure states in the lab. So now let us ask a question. Till now, I was having a 2-qubit system. So 2 particles were there. I know the state of those 2 particles, and I was creating a composite system. But now I have a experimental setup in which I am generating 2-qubit system. Okay. Now, can I obtain the state of a single particle associated with this 2-qubit system? Is the question. If there is a 2-qubit composite system or a joint system, where what are the states of the individual subsystems? So can we gain the knowledge about the subsystems is the or local density matrices is the question. If I have a density matrix, okay, if I have a density matrix rho AB which belongs to psi A tensor psi B, then psi A, what is the density matrices of the local density matrices or state of the subsystems is what I am seeking here. So this can be obtained by something the procedure called as the partial trace. The partial trace of rho AB with respect to the subsystem A is denoted by trace with respect to A rho AB, and is defined as if you have pros. If you want to know what is state rho B, then you have to remove the state A from that particular composite system psi AB. Okay, so this can be like even if you consider the language of matrices in terms of summation, you can rewrite, you can exhibit this particular expression. It is like summing over all the basis vectors with respect to A. You are throwing away A particle, so therefore you have to consider the summation or the expectation value of rho AB with respect to this particular states of A. So where you have all the i's are from the Hilbert space of the A particle. Similarly, trace, if you want to know the state of the particle A, you can define that this you have to sum over all the B Hilbert space corresponding to B and their basis. So let us consider an example which will be more clear to you. If you have psi AB, which is defined as half times 0 1 plus 1 0, then the density matrix can be written like this. So density matrix is nothing but the outer product psi AB, tensor product psi AB. Okay, so therefore you have your density matrix written like this, which will have 4 terms. So now if you want to trace out, I have this definition, trace out the particle B, and I want to do, write only the density matrix or the state of subsystem A, then we have this particular expansion. Now I'm just placing this rho AB structure here in this expression. I'm just placing rho AB here and then rewriting this expression. To evaluate the first particle, just first term, just consider this first term. So now I have already been emphasizing that the position of the particle is very important, and they corresponding to the particle A and particle B. This corresponding to particle A and particle B. Remember, we have closing, our inner product is taken with respect to B. So therefore, I'll expand this one. So I'll write in terms of tensor product, and I see that these are the form for this particular stage. Now, you should know that this is with this here I am closing or taking an inner product of a basis corresponding to B Hilbert space or particle B with the particle with this composite system. So therefore, rho A is kept undisturbed. Now rho 0B antiquate is closed with the 1B here. I hope you people are getting this one. So 0A tensor product is taken with the, since this belongs to the Hilbert space B, therefore I have to choose a particle whose basis is also from the same Hilbert space. So therefore I have 0, 1. Similarly, I have here the 2 particles. A is untouched, and then B Hilbert space, B Hilbert space. So therefore I have. Now I know that this within this Hilbert space, 0 and 1 inner product will be orthogonal state. So therefore this will be 0, and hence we will have 0A particle outer product with coefficient 0. This means that when you write a density matrix A, where I have basis 0, 0 and 0, 1. Now this one will be my coefficient of 0, 0 here. So therefore this term is. Likewise, you have to calculate each and every term. If you evaluate, there are 8 terms, so therefore you will get something here, 2 terms added here like this. So here you will get 1, here you will get 0, 0, you will get 0, 0, and therefore here you will get 1, 0. So if you, all the 8 terms will add up to give you 4 terms in this one. So similarly, if you want another example, I have worked out here. So where you will get coefficient as 1, and this is corresponding to the 4th term of that particular trace expansion. So now get this expression. So half in the before we have the 1 by root 2 multiplied twice, so therefore we have a 2 here, and then I have giving you 1, and then this one. So therefore you can write the subsystem density matrix. So therefore you have, since we started with a pure state, so that you all know that. Therefore, the subsystems of a pure state will always have same eigenvalue structure, or you can, since I have only 2 qubits here, you can see that even rho B will have the same density matrix. So try to do this exercise 1 or 2. Practice makes one better in understanding the things. So therefore you try to expand this one carefully, and then later on it will be easy for you. Like once you are familiarized with the inner product of the corresponding basis vector corresponding to the particle in the given multi-qubit state, then throwing away the particle will be easy. So for example, if you have a 3-qubit state, and if you want to write the, there are 3 qubits, and I just want to I want to ignore the second and third. I want to write only the state of the first particle. Then we use this expression. Where here you can see that the summation is summation is run over ijk and jk here, and then you are left with alpha prime, which corresponding to the subsystem A. Similarly, you can define this partial trace operation when you want to get the only the density matrix corresponding to the 2 particle, where you throw away the 1 particle. So whenever, how many number of particles you have to throw away, that many summations you have to incorporate here. So try this particular expression for 3-qubit states, a simple 3-qubit state, that is the GSS state. It will make you clear on the operation of partial trace. If rho AB is equal to rho A tensor rho B, that is, if you have a subsystems which can be written as the tensor product, then subsystems are rho A and rho B. And you know everything about this particular subsystem. Whenever you can write a density matrix as a product of this subsystem, you know everything about this particular. For example, if you have a composite system which is given as 1/4 times I4, then you can see that the subsystems can be written as the tensor product of these 2 subsystems. So, and another important property about this partial trace is it's a linear. It's a linear operation. That means if you have 2 terms, you have to first you can do partial trace of the particle in the first term, and then partial trace of the subsystem that you have to throw away in the second term, and then you can just add. So you can see that if you, for this example, you can see that the partial trace can be worked out. Earlier I have already shown that this partial trace is will give you half times 0 0 plus 1 1 for the sign minus state. And you can see here it is just throwing away a particle. So since this state can also be written as 0 0 tensor product 0 0, so it is just throwing away the second particle. So therefore I have this one. So it is just addition, linear addition of the terms. So 0 0 will add up with 1 coefficient will have 0 0's coefficient 1 minus p will add up with p by 2 and will give you this expression. So you can see that this particular state will also give you same rho b. That is, if you have 2 particle A and B, you remove B or you remove A, the state of the system will be always same for this particular system. So again, when it comes to 2-qubit systems, there are some things that I am not dealing here because of the time constraint. Probably you people have to understand, if at all you want to understand entirety of handling 2-qubit system, it is better that you try to read and learn about the Pauli matrices, their properties, operations as unitaries. How do they operate as a unitary operations? And there is one particular aspect called as a Gram-Schmidt decomposition, in which if you have any set of non-orthonormal linearly independent vectors, that is, they are not a basis vectors. You have a set of vectors, but they are not basis. If you want to convert them to basis, you should know that these non-orthonormal set of vectors should be converted into orthonormal basis. There is a procedure identified for this particular condition, and this procedure is called Gram-Schmidt decomposition procedure. Please try to learn about this. And when it comes to measurement, we have 2 systems. We have to make a measurement on the 2 system. Either you may measure on the first particle, or you may make a measurement on the second particle, or you may make a collective measurement. Then there are certain governing rules. Outcomes. How do we expect the outcomes on? So those measurements should be understood. So there are projections measurements, and there is a difference between projective measurement and POVM. All these things has to be learned. Try to learn so that you the entirety of handling to when you try to learn more about the quantum information are. Now I am ready to define the quantum entanglement to you. Let's see what is quantum entanglement. Now you have a composite system or joint system which is given by a tensor. I have 2-qubit quantum state which belongs to H8 tensor H. So I will call let the 2-qubit system, one of the particle be identified being present at Alice, and the other particle is present at B. Okay, so the state of Alice is given as psi A. The state of the particle with respect to Alice that is present in the hands of is psi A, and similarly the state of the that is of the particle that is present in with let us call psi B. Okay, now I have the psi A psi B as the composite state of the two particles. Okay, so now Alice prepares her state in psi A, prepares the combined system is given by psi A tensor psi B. Now, a quantum system that can be written as the tensor product of its subsystems is called the product state. So you had psi A B, which can be written as psi A tensor psi B. Okay, this is the tensor product, right? So therefore, if you can write this in this structure, that means you have a product state. Any pure state whose local density matrices are pure is called, because I told you earlier also, when I write rho AB as equal to rho A tensor rho B, I know everything about A and I know everything about B. So therefore, logic applies where I know everything about psi A and psi B individually. Therefore, I can write the composite system as the tensor product of those two states. A state which cannot be is called the entangled state. The simple straightforward extension to the entangled state. I have a product state where the composite system can be written as a product state of the local states, and I have an entangled state which cannot be written as a composite state. So if you want to prove this one, it is straightforward. Since I have to cover, okay, I can do this one in a minute or so. So if you have 5 plus, which is one of the Bell state, and you try to assume this 5 plus to be as the product state. Okay, let us try. We are trying to prove whether this is true or not. Okay, so if I have this state, I will try to write this state as the tensor product of two possible states, and then identify that particular tensor product of the two states that is given by equation 2. Now compare equation 1 and 2, and so that you will see that if the state 5 plus can be written as the tensor product, then the coefficient should be equal, right? The corresponding coefficients of the 2-qubit states. Okay, so 0 0 is equated with 0 0. So AC plus BD 1 1 will 1 1 coefficient is BD is equated with the 1 1 coefficient over here, that is 1 by root 2, and similarly AD and BC are identified to be as 0. So these 4 conditions will tell us that either A should be 0 or D should be 0, or B should be 0 or C should be 0. But here it is fitting well. So all the 4 conditions cannot be satisfied. Therefore, you cannot write a composite state 5 plus in terms of the product state of the 2 states, 2 qubits. So hence we have that entangled state. This is an entangled state because it cannot be written as the product of the tensor product of the 2 subsystems. So for example, if you have a state which is 0, 0 plus 0, 1, then surely you can write this one as the 0 plus 0 plus 1 state. So therefore, you have a tensor product of the states. So hence, this will be a product state. So try to create some examples on your own and then try to understand what it means to, as soon as we write a this structure like this, you should be able to understand whether it is a entangled state or a separable state. Okay, by doing so, many more examples probably try to identify with ease about this. Now I will to see I am trying have a density matrix, make a partial transpose operation, find its eigenvalues. If the eigenvalues are found to be non-negative, then we have the positive under partial transpose operation, or a state is said to be PPT. Otherwise, the state is said to be non-positive under partial transpose, or NPPT, or NPT in general. Okay, so this PPT and NPPT is very important, or even this one is NPT most of the times. So this is very important feature when it comes to partial transpose operation. Okay, and this partial transpose operation also has a group theoretical implication. Okay, so which maybe some you people, if you want to know more about this partial transformation operation, you should try to dig on this particular topic in various resources, and hence you can learn more about what actually means by partial transpose operation, what is group theoretical meaning of this one, and so on. So I'm left with characterization and quantification of quantum entanglement, which I will take up in the next session. That will be on 12th and 12th October, 1 o'clock session, right? 1 to 3 session. So I'm now ready to take some questions if there are any questions. So I can see there are some one question in the chat box. So are the states of particle inside the universe always mixed? Yes. If you consider the universe as a pure state, then of course all the states which are subsystems of the universe should be mixed state. That's why I also emphasize that in the lab always we create a mixed state, because there is no way that a subsystem or a particle or a quantum system can be not influenced by the environment. But however, we know we have ways to overcome the this one, like what we try to do. There is something called as tomography of the system, of the quantum system, which experimentalists often try to do to emphasize or nullify the effect of the environment, even at least on paper. For nodes, I will try to yeah, I will ask organizer to give a link to, I will upload elsewhere in the slides and maybe in the Google Drive or somewhere, and then I'll ask the organizer to give the link to the in the description below, or you can come to my webpage and then maybe try to get it from there as well. I haven't. Isn't there is a question here? Isn't the partial trace is positive only in case of non-entangled states? This is exactly true, but I am not. I haven't used an example, therefore I'm not more about this one. Maybe in the next session I will tell what is the link between this partial transpose operation and. Jatin, what are you asking? Can you please unmute and pose your question, please?
So I was you said that all states in the universe are mixed state. Can you give a physical explanation behind it?
See, the first and foremost, physical pure state means all the information is known to us. Okay, so if you consider any subsystem, there will be always an external influence or environmental factors will come into picture, right? Only if you write for the entire universe, there is then there is no environment affecting the universe, right? In that sense, when you say that the ideal pure, see, remember this is an ideal situation. The ideal state is can be removed for the universe. Whatever we have, of course, daily people are creating pure states in the lab. Okay, so those pure states to us, you can say to some extent they are pure pseudo pure states in a when it compared to the ideal situation. That's what I mean. Is this clear, Jatin?
Yes, sir. Thank you.
So, Dr. Prabhu, this is Baladitya.
Is prime. What
Hello.
if the I am just reading the questions one by one after the this one. Prem Kumar is asking, how can we divide quantum system into sub dimensions is prime? Yeah, that is a nice one. I will be in the next class. I will try to address this one because we have different ways to address the entanglement between these subsystems. It is not quite simple. It doesn't depend on whether it is a like a total system is prime or not. Maybe pick up the quantifying the entanglement in the multi-qubit system. What if the universe has prime number of dimensions? I really don't know. Maybe you have to wait for next lecture so that you can understand this one. I think I have covered all the questions in the box. If anybody has to or verbally ask me any questions, please unmute yourself and then pose your question. Thank you.
Prabhu, Dr. Baladitya Suri from IISc had a question.
Hello.
Professor Baladitya Suri, please.
Hello, Dr. Prabhu. It was a very, very nice, very lucid introduction to entanglement. So I was intrigued by the statement you made about the universe is always in a pure state, right?
Yeah. As I was telling earlier, because it is an ideal situation that we are talking about. So
okay, so yeah, because the way we have, at least the way you have introduced mixed states, is you take a pure state and you take a partial trace of it, and you have shown that a partial trace of a composite mixed pure state is always a mixed state, right? Is there any fundamental reason, is there any fundamental argument which people have used? Of course, it's only a hypothetical argument that the universe entirely considered entirely should necessarily be only in a pure state.
Yeah, because see, whenever we have if you take any subsystem of the universe, then it should be having the another subsystem associated with that one, right? So in this way, but if you consider to write a state of the universe, then you don't have anything else left. So there is no question another subsystem for the parallel to the universe. So
okay, so to rephrase my question, so yeah. So my question, so my question is, so
please go ahead.
Mixed states are always, what if I understand what you're saying correctly, you're saying that a mixed state occurs only when as a sort of in physical systems, it occurs only as a partial trace or a
of the
of a
see,
pure
for
state.
example, like any pure state in the labs.
Mhm.
So it should be a subsystem of the
Okay.
one of the subsystem of the whatever is left out as the environment, right?
Uh-huh.
When we do tomography of any state and we write density matrix on this one, we always write with certain probability what is the state that has come, like 0.9999%.
True,
If
true,
you
true.
write the, if you
Yes,
see
yes.
density matrix of the tomographic picture that people will associate when they present their experimental, they always,
Correct.
they will not write it as one directly, right? So if it means,
Yeah, yeah.
if it is one, then I will say that it's a pure state. So we always try to
Correct,
go
correct.
as close possible to pure state representation.
Okay. Okay.
In that way, I am telling like people should know that the pure state means something. It cannot be generated in that. We always generate a mystery. Always say environmental. The other way is to put is that we a quantum system with, right?
Uh-huh.
Yeah, is it clear? So
Yeah,
what
yeah,
I
yeah.
am trying to emphasize here.
Yes, yes, yes. Okay. Thank you. Yeah.
Okay, thanks for the question. Is there anything else? Anybody has any query? Please let me know.
Excuse me, sir.
Yeah, please, Prem Kumar. Go
Sir,
ahead.
this is Prem Kumar. Suppose we have a 5-dimensional quantum system and we want to study it
Yeah.
as a qubit system using qubits.
Huh.
So I think 2 qubits will not be sufficient, but will we use 3 qubits? We'll have 8 dimensions, eight dimensional vector space, Hilbert space.
Okay, I am
So
sensing what you mean. Yeah.
then to study that 5-dimensional system, we'll be using 8-dimensional
See,
Hilbert space.
you are getting confused with the dimensions, with the number of superpositions that we when you expand the system. Okay. So when we write, maybe I'll try to write here. See, if I have a qubit, I will always write in terms of B1. So this he is made up of Hilbert space 2. But this is a qubit. When I have a 3 qubit, A, B, C are the particles. Then I have A 0, 0, 0 plus 0, 0, 1 plus C plus so on. There will be 8 terms, right? So when I have these 8 terms, this means that this particular state belongs to my Hilbert space, which is given by H2 tensor product H2 tensor product H3. Okay. Oh, sorry. Since it is a 3-qubit system. Okay. This does mean that my space is giving me 8-dimensional superposition of the states. Okay, is that clear?
Yes, sir.
Kumar?
Yes, sir.
Yeah. Anything else? Jatin has one more question. Is a truly isolated state inside the universe can be pure state? Like experimentally, we don't have any way to get an ideal pure state. That's what I am emphasizing upon. Is this thing? We are going to, yeah, we experimentally, we are trying to close to pure state. never a complete pure state. You cannot see, if you have any quantum system, you cannot have a isolated quantum system at any moment. So when you write the state of the system,
I think we have an idea. Is it a pure state?
that's what we do. All experiments we're trying to do is that by minimizing as much noise as possible that will be accumulating in the experiment steps.
Okay.
So anybody else has any questions, please unmute yourself and then let me know. If there are any questions that you want to write over email, please let me know by email. I will be very happy to help you with that one. I think Anindya, you have to take over now.
So, just a minute. Hello, am I audible?
But it's, I think, so. Thanks a lot, everybody. So, bye.
Thank you, Prabhu.
Yeah, you're.
Thank you, sir.